what I'm going to try and do today is explain exactly where the trigonometric functions, the graphs of the trigonometric functions come from. So in order to understand them, we have to return to the unit circle in the Cartesian plane. So the definition of the unit circle is that it just has a radius of 1. I've drawn it with the center being at the point 0, 0. So this then therefore has to be the coordinate 1, negative 1, negative 1, and 1, because it's the radius and we are talking about the unit circle, which has a radius of 1. So what we're going to do is we're going to track some point on the unit circle, and we're going to the where this point lies is going to be determined by the angle that this line makes with the positive x-axis. So we can call this maybe angle x. Now, angle x creates or subtends this angle, and because of the angle created, we have this point, and we can call this point P. It doesn't really matter what it's called, but more importantly, we're interested in what its coordinates are. So in order to determine its coordinates, what we can simply do is we can drop down a perpendicular line, and we can create a right-angled triangle. So we need to remember that this is the unit circle. So this circle has a radius of 1. Now, if we could determine this length over here, then we could determine what the x-coordinate is, because it's from the origin to this point. The x-coordinate would be the length of this line. So if we can determine the length of this side, we can then determine the coordinate of this point, or the x-coordinate of this point. So if we have a look at this side, it happens to be the adjacent side to angle x, and we know the hypotenuse, and we know a ratio for adjacent on hypotenuse. It's cos of x equal to adjacent on hypotenuse, which happens to be 1, and the nice thing is anything divided by 1 is itself. That tells us that the length of this side is cos of x, right? Because the hypotenuse happens to be 1. That's the wonderful thing about the unit circle. In the same sense, we can say that this height here would be sine of x, because this happens to be the opposite side to angle x, and the hypotenuse happens to be 1. That then tells us that this coordinate P would then be cos of x sine of x. So as we change angle x, we would change where point P sits on the unit circle, right? So the bigger the angle, the further the angle would sit from the positive x-axis, etc. Okay. So where our trig functions come from is we are going to independently look at what happens to the position of point P in either the height or the horizontal shift from the center or from the origin for each function. So what we'll do is we'll have a look at sine of x first. All right, it's normally the function that we look at, or the function that we learn first. So what we mean here is we're going to look at what happens when we change the value for x. So we're going to map this on x. X is an angle. We'll look at it in degrees at first. We'll start off at 0 degrees. We'll look at 90 degrees, 180, 270, 360. And we can keep going if we really wanted to, if we wanted to do more than a full revolution. So what we're going to do is we're going to track the height of point P. So if I isolate point P, remember that this has to stay on the unit circle, right? If the angle was 0 degrees, right? 0 degrees from the positive x-axis must mean that it had to sit on the x-axis, right? And you can see that if we were to measure the height, the vertical shift, well, we haven't gone anywhere. We're at the origin, okay? And so our position would be at 0. So for sine of x, right, if the angle is 0, then the value is 0, right? There is no height, Right? Y is equal to 0 at this position. Now, if we had to create an angle greater than 0 and we went all the way up to, say, 90 degrees, we'll notice that the height now of point P would be 1. All right, it is 1 unit above the origin. All right, so at 90 degrees we would have a value of 1. So let's just fill in these values here. Continuing, we can take our point P and we can continue moving it around the unit circle till it got to 180 degrees. And we'll see again, we're not measuring that it's at -1 because that's the horizontal distance from the horizontal, from the origin. We're interested in the height, all right? And it is on the x-axis, so it has not shifted vertically at all. So we're back at 0. And now we can continue moving around. If we get to 270 degrees, we're back at -1. And finally, if we moved all the way around a full revolution, 360 degrees, we're back at 0. Okay? And so if we had to join the dots, as we say, you would find that we create a curve very similar to this. Okay, and that is the sine wave that is generated. Now, obviously, you can work out that we can continue rotating. We can make angles greater than 360 degrees. However, we would get the same shape. And so sine is a periodic function. It has a period of 360 degrees. So every 360 degrees, it would repeat itself. And that's obviously the base sine unit. So this is the graph of y equal to sine of x. Now, in exactly the same way, we can now map cos. Now, cos is not looking at the height from the origin. It's looking at how far left and right we are. So if we start at an angle of 0 degrees, which is where we are now, we'll notice that point P is all the way over here at +1. So we're all the way up here at 1. So let's move point P. So if we move point P all the way around to 90 degrees, we'll notice that we're now on the y-axis. And this is the point where x is equal to 0. So at 90 degrees, we are at 0. And if we rotate some further all the way to 180, we are at -1. And if we go around to 270, we're back at 0. And finally, if we finish the revolution to 360 degrees, we're back at 1. Okay, so again, if we had to join this up, we would create a not as pretty as the other one, but you get the idea. Again, it's if we had to continue increasing the value for angle x, we would just repeat the same looking graph. And cos of x, therefore, also has a period of 360 degrees. Right, so this is the period. Right, how long it takes for the graph to repeat itself. This is the graph of y equal to cos of x. Now, there is one other trig function that we are usually accustomed to, and that's the graph of tan, right? And when we think about tan happens to be adjacent or opposite on adjacent. So if we think about the ratio tan of x, right? Tan of x is just opposite over adjacent. So if we go and have a look in our triangle, the opposite side here just happens to be sine of x, and the adjacent side is cos of x. And believe it or not, this is actually a fundamental trig identity, that tan of x is just sine on cos, but we'll learn more about that later on. For now, just to get some understanding of what the graph might look like, we can say that we can look at the values of sine and cos at 0, 90, 180, 360, and we can get some indication of what the value of tan would be. So let's start at 0 degrees. At 0 degrees, sine is 0 and cos is 1. And so tan would be 0 over 1, which is just 0. Right, so I'm going to label this as 1, negative 1. Here we're going to have 90, 180, 270, 360, etc. All right, at 90 degrees, sine is 1 and cos is 0. So we have 1 over 0, but we cannot divide by 0, and so we have a point on the graph which cannot exist, and we call this an asymptote, and we'll represent that with a dotted line. Okay, so this is a part of the graph where the graph cannot touch because it cannot be equal. You can't have 0 on the denominator. Now at 180 degrees, sine is 0 and cos is negative 1, so we have 0 over negative 1, which is again 0. Then we have 270 degrees where sine is negative 1 and cos is 0, so we are dividing by 0 again. And we can't do that, and so we have another asymptote at 270 degrees. And finally, at 360 degrees, sine is 0 and cos is 1, so we have 0 over 1, and so we are back at 0. Now, obviously, this is very unuseful to us because all we have are 2 asymptotes and 3 points, and we have no idea what the graph is doing, all right? And so what we can do is we can look at values in between to give us an indication of what the graph might be doing. Okay, we know it's going to approach an asymptote from either side. So you can stick into your calculator what is tan of 45, and you'll find that tan of 45, we should know as an exact value, is 1, right? And so what's going to happen is this graph is going to start at 0, go through 1 at 45, and approach the asymptote but never touch it. And we can do the same thing, right, for the other values in between 90 and 180, and we'll find that we get negative 1, we'll get positive 1, and we'll get negative 1. And so what ends up happening is we end up with a graph that has a shape like this. Okay, and we should actually be familiar with the shape from our IGCSE. So this is where the trig functions get their graphs from. They come from the unit circle. As we rotate a single point around the unit circle, we end up with the sinusoidal pattern for sine and cos, and we end up with this pattern for the tan graph that we see below. Now, as you can see, it only takes 180 degrees for the tan graph to make one copy of itself. So these are what we call the vanilla or the base trig functions. And what I'm going to do is just quickly clean up this cos graph. All right, here we have a much cleaner version of the cos graph than before. Okay, now what we're going to look at next is what happens when we start changing values in front of this equation. Okay, because what we've got here are the base graphs. So we've got sine of x, cos of x, and this is the graph of y equal to tan of x. And just like every graph, we can apply some kind of transformation to it, and we can move it, stretch it, etc. And we're going to look at how that works with trig functions.